Okay, hi Year 10 and 11. Today we are finishing off the last couple of exercises in a differentiation topic before we move on to Chapter 9, which is extending our calculus. So 8K and 8L are looking at continuity and differentiability. So a function is said to be differentiable if it can be differentiated at every point in the function. Now, so far, I guess all of the functions that we've been dealing with have been able to be differentiated, and that's not always the case. There are functions that exist that at certain points we cannot differentiate them at. So that's what this topic is basically dealing with. So we'll say that again. A function is said to be differentiable, it's a hard one, if it can be differentiated at every point in the function. So as I just said, there are going to be some functions where some points within that function we are not going to be able to differentiate, so that will be a non-differentiable function. There is a simple test to see if a function is differentiable. Okay, first one. The function can be drawn without lifting the pencil from the paper. That's what we would call a continuous function. So if I could draw a function, that would be this one down here. Start up here, draw along, draw up, draw up. I can draw that without lifting my pencil off the paper. That's going to be a continuous function. The second thing is, if the curve is piecewise, which we're going to have a look down here in a moment, where there's different graphs for different domains within the graph. So if it's piecewise, then the resulting curve must be smooth. So if you have a look down here at this graph, it's not smooth, is it? It's pointy. So if it's piecewise, the resulting curve must be smooth. That is, when two different curves combine, they share a common tangent at the join point. So that's not going to happen down here because I'm going to have different tangents going different ways at the join point. And that's what we're going to have a look at first, are the piecewise functions. We looked at piecewise functions earlier on a little bit. Let's have a look at them again. So a piecewise defined function has different definitions in different parts of its domain. These are combined to make the complete function. So this function has three different graphs, or three different parts, depending on where x is. So we've got x less than or equal to 2. So from this point onwards, down to the left, we've got x greater than, x less than or equal to 4, So we're from here, this point here, down to here. So that section has a different graph. And for x less than 10, this bit in here. So we've got different function parts for each domain of x in there. So the first one, minus x plus 1, is, let's draw some colours in there. Let's do this one. So minus x plus 1 is this part of the graph in here. Okay, minus gradient, moved up, plus 1. Yep, that looks right. That makes sense. That's the first section. But when x is less than 4, but it's not less than 2, so that's in this part here, we've got this graph here. So x minus 3. So if you think of what our graphs looked like when it was y equals mx plus b, it's a 1 gradient, and it's going through minus 3 if we were to move that down there. Yep, that looks pretty right. That's that one there. Lucky last, we've got, oops, I might make that one yellow for you to see. The lucky last bit is this section in here. This last part of the graph is when x is less than or equal to 10, and we've got minus x over 6 plus 5 over 3. So three very different functions joined together to make one whole, and that's what we call a piecewise function. So what we, I guess, notice on the graph is the graphs are joining at these 2 points here. Okay, so they join at x equals 2 and x equals 4. And we're going to test to see if this is differentiable and continuous by looking at those 2 points that were described up above. So let's have a look at the first one. The function can be drawn without lifting my pencil from the paper. So I can do that. I can go right along those. So it's continuous. The function keeps going. There's no gaps in that function at all. Part 2, if the curve is piecewise, which is one of these, then the resulting curve must be smooth. So if our curve had gone a bit like that instead, I'd call that a smooth function, but it is not. Ours are very sharp pointed down here. It's not smooth at all. And it says that is when the two different curves combine, they share a common tangent direction at the join point. So the join point here at x equals 2, if we're looking up here, we'd have tangents going this way. We've got tangents going this way. So when x equals 2, we do not have a common tangent at that join point. Same as up here, the two lines have tangents that would be going in different directions. So we would say this one is not differentiable at the join points, x equals 2 and x equals 4. However, the first part of the graph is differentiable, the middle part is, and the last part is, but where they join is not. So by definition, this is not a differentiable function. So let's go down a little bit on your booklet. Here's some example curves. The first one here we're quite familiar with, xy equals 1 over x. It's a hyperbola. We've been differentiating curves like this, which is y equals x to the minus 1. We've been able to do that. The curve is smooth, isn't it? If you put our pens along there, it's nice and smooth. However, the curve has asymptotes. So let's have a look at those 2 points up above. We were saying, is our function continuous? That was our first point. Well, it's not continuous, is it? Because if I was to draw along this curve here, I have to lift my pen to get to the next part of the curve here. So this is not a continuous curve. It is smooth, but it's not continuous. And we know what the asymptotes do. The curve does not ever touch those asymptotes. So there is that discontinuity at x equals 0 and at, I guess, y equals 0 as well. It's differentiable everywhere except at those points. So have a look at your middle curve here. Now, again, another one that we're really familiar with. It's y equals x squared. It's our parabola. This one is only cutting at the point at the origin at 0, 0. So the curve is smooth. So if you run your pen along that, there's no sharp edges. It is continuous everywhere, so I can draw that without taking my pen off the paper. There are no breaks in the curve, no sharp edges. This one is differentiable everywhere, and we've been doing these ones for a few weeks now as well. So let's have a look at our last curve here. It's a piecewise curve. It's got one section that is a parabola. So for x less than or equal to 0, down here, we have got the curve y minus x squared. So we've got an upside down parabola cutting at minus 2. But when x is greater than 0, our curve turns into a straight line, which is y equals x plus 4. The curve is continuous, so I can go along it with my pen. Don't have to take that off the paper. So it's continuous, but it's not smooth at that point there, is it? If you have a look, it changes direction. So if I'm going along here, bump, it changes direction. So it is not smooth. So it's not going to be differentiable at that point there when x is 0. Okay, so it's differentiable everywhere, but at that point x equals 0. And that's the definition. Look, that's the second one up here. If a curve is piecewise, then the resulting curve must be smooth. Ours is not. That is, when the two different curves combine, they share a common tangent. So if I was to draw tangents on that curve, all the way along like this, they're going to have a change. A tangent from this curve is not the same as the tangent from that curve there. So it's not smooth. So that is not differentiable at x equals 0. Okay, so let's go and have a look at some examples and see if we can have a go at working out some of these ourselves now. And here's our first one. Okay, so there's a function on the side over here. It's a piecewise function. For values less than x, we're looking at 2 to the power of x. For x equals 1, it's just x, so 1, sorry, and for x greater than 1, it's x squared. Now, one way we could deal with this piecewise function is to draw it. And that wants us to do that for part 2. We, however, can, for part 1, and let's read it, do something else. So it says for the piecewise function shown, A, establish whether the graph is continuous at x equals 1. So if a graph is continuous, then it moves from one point to the other. I can draw it without taking my pen or pencil off the paper. So that means my values at each point along that graph at x equals 1 need to be the same for each of these. Okay, so let's have a look. So let's work out what 2 to the 1 is. Oh, we've got 1 equals 1. That's an easy one. And 1 squared. So the first part, 2 to the x, which is 2 to the 1 is 2. We've got 1 equals 1 and 1 squared is equal to 1. Okay, so because for each of those functions at the value x equals 1, they're not all equal, so we've got a 2 and a 1 and a 1, then the function isn't continuous at that point. So all the parts of the graph do not join continuously. There's going to be a break in there. Okay, these two are going to join, those parts there. Okay, but this top one is not going to join. So there's a break in the graph somewhere, and we should be able to find that when we sketch that graph in a moment. So the graph is not continuous at x equals 1. Let's draw it and find out. Draw yourself a set of axes to start with, and we'll see if we can get you to have a go at drawing it while I do the same as well. Okay, so let's draw that graph. So we've got 1 being a major point here, so I'm going to put 1 down here on my graph. What we're going to do is we are going to sketch our graph and see what it looks like. There we go. So I'm just fixing up the screen there for us. Okay, so when x is equal, I'm going to do the middle one first. When x is equal to 1, our function is equal to 1. So there's a dot there, and there's a 1 there. Okay. When x is less than 1, so we're down this side over here, it's going to be an exponential graph, so 2 to the x. But we know that 2 to the 1, it equaled 2. So up at this point here, it's not equal to 1, it's less than 1. That point there, when it's equal to 1, so 2 to the 1, is not actually included into that graph. Okay, so we put an open point in there. And it's going to be an exponential that we're going to draw down there like that. Okay, so it's going to go through. It's going to look like that. If you forget what your exponentials look like, you can always pop points in. When x is 0, 2 to the 0, I get 1. And remember that it's decreasing all the way along there. So you can already see now that we can re-answer our part A, determine whether the graph is continuous at x equals 1. Well, there's that little gap in there. Let's have a look at the last part. When x is greater than 1, we've got x squared. So it's going to be a parabola, basically, after that bit. And that's our x squared. That is our piecewise graph for part B. Let's have a look at part C. We want to do the domain, and we want to do the range. Okay, so let's have a look at our x values for the domain. Remember, domain is x, y, range is our y or our f of x value. So the domain, we can have all values of x occurring along here, all values of x occurring even along here, because we've got one of those points here, and all values of x occurring along there. So our domain is going to be all real x values. That's going to be okay. Our range, however, let's have a look at that. What's our range going to be? So we can have values occurring along here for all values of our y or f of x down to 1. What happens below 1? We can have values for y or f of x only going down so far as the x-axis, because this x-axis would be an asymptote to our 2 to the power of x. So that line here is never going to actually touch our x-axis, and the formula for our x-axis being y equals 0 means that we can only have values of y that is greater than 0. Not equal to 0. Okay, we're nearly there for this question. We're looking at part D. Where is this function differentiable? So, if you have a look at the diagram, there is smoothness in these curves, but there's a break in here. I can't draw here and continue onto this graph without removing my, with leaving my pen on the paper. There's a break here. It's not continuous. It's not going to be differentiable at x equals 1. And that's our solution for that one. So we'll say not differentiable at x equal to 1. To be 100% correct, I probably should put for part D that it's differentiable everywhere except, or x equals 1. So you could answer it both ways. Probably should say everywhere as well, except if x equals 1. Okay, let's have a look at the second one. Okay, part 2, it says test the function for continuity and then differentiability at x equals 0. Then sketch the curve and write down its domain and range. Okay, so here's our function. For x less than or equal to 0, we're equal to x. And for x greater than equal to 0, we're equal to x minus x squared. Okay, so let's test for continuity first. So let's do that. So if there's continuity, then at x equals 0, there should be the same value of the graph. So there's not going to be a break and there's not going to be different values for each of those. So let's just test what happens at x equals 0. Because that's what it would like us to do. And that makes sense because our points of the function, our function changes around that point x equals 0. Okay, so at x equals 0, f of x equals, for x, it's 0, and for x squared minus x squared, we get 0 minus 0 squared, which is 0. And I probably should put equal signs in there, not my arrows, because we're not doing limits or anything like that. Okay, so at x equals 0, the function has the same value. It's going to be 0, so it's continuous. There's no break in that function there. Let's check for differentiability at that point as well. It's a big word, differentiability at x equals 0. The best way to test for that is to differentiate at each part of the function. Pop in x equals 0 and see if we actually get the same value of the gradient at that point. If we're getting the same gradient at x equals 0, then the second point is up here, is met. So we already met our first one. It's continuous. Our second one, it's piecewise. It must be smooth. Well, we can't see that yet. We might be able to see that when we draw it. When the two different curves combine, they share a common tangent direction at the joining point. So I will be testing that by having a look at differentiating at x and differentiating at x minus x squared, putting in x equals 0 and seeing if we actually get the same value. And that will mean that if we do, we'll get the same gradient of the tangent at that point and it will be differentiable at that point. So let's do that. So let's differentiate the first part. Let's work out what ddx of x is. It is going to be equal to 1. Let's work out what the differentiability of x... Oops, hang on, I've made a little mistake up here, haven't I? What I popped in here is I popped an extra squared in there. Sorry, guys, if I've confused you there. That should be an x squared. I'm going to differentiate now x minus x squared. And what that's going to give us is 1 minus 2x. Let's sub in x equals 0 at each of these. I'm still going to get that ddx of x is 1. Because I can't pop any values in because there's no variables in there. And the derivative of x minus x squared at x equals 0 is going to be 1 minus 2 lots of 0, which is also 1. So these values are the same, which tells me that at that point x equals 0, it is a smooth curve. The gradient of a tangent drawn there has the same value at that point for both of my functions, so it is differentiable at that point. I'm going to write that down. And now let's have a look what it wants us to do as well. Then sketch the curve and write down its domain and range. So let's do that. Pop in some axes. And have a go at drawing it. So everything's rotating around our point x equals 0. So it's rotating around there. So let's go and have a think what our graph looks like. For x less than or equal to 0, our function is equal to x. So y is equal to x for x less than or equal to 0. So from this point onwards, we've got y is equal to x. So our graph will look like that. But when it gets to here, 0, for values above that, it's going to look like x minus x squared. Okay, well, x minus x squared, that looks like, let's factorize it. It's going to be 1 minus x, so it's going to cut the x-axis. If we set that to 0 at x equals 0, which we know already, and x is equal to 1. Okay, so let's go back and pop those onto our graph. X is 0, x is 1. So we already know our x is 0 point because we've already popped that in there. Our 1 value here is giving us the other 0 for our parabola. So from this point onwards, it's going to look like this. Now, it wants us to draw it in a little bit more detail than that. So we need to find this point here. We need to find this point here. Probably the easiest way to find the point in the center here is it's halfway between 0 and 1, and it's a half. But what I'd like you to also think about is it's also the x-coordinate of our stationary point or our turning point. And what happens there? That's when our dy dx is equal to 0. And we've already differentiated here. So our ddx of x minus x squared is 1 minus 2x. So if I figure out where 1 minus 2x is equal to 0, what I'm going to end up with is 1 equals 2x, x equals a half. So I could have found that as well via that way. The other way was minus b over 2a. There's so many different ways we know how to do that one now. But we also want to find our point. We need to find the y coordinate or the f of x value for that. So we're going to pop that back into our curve. Now we're saying x is a half. So we've got a value of x that is bigger than 0. So we want to pop it back into this graph here. So x minus x squared, it's going to be a half minus a half squared, which is a half minus 1/4, which is equal to a quarter. So if we go and pop that back onto our graph there, we've got that other coordinate. It gives us the whole point. So the point there's a half and a quarter. Now, have we answered our question yet? I don't think so. It wanted us to also write down the domain and the range. So let's do that now. So remembering the domain is the x values. So have a look along here and see what happens to our graph. We've got values of x possible for all of our graphs. So we're going to say our domain is all real x. And our range is our y. Our y, well, the biggest y value is up here. And we can't have any y values above that. So we want values of y that are equal to a quarter or less. So our y, our range is going to be y is going to be less than or equal to 1/4.